In Chapter 6, we're looking at Lesson 6 today, talking about function operations. Whenever we combine two functions where the output from the first function becomes the input for the second function, we call that a composition function. Here's an example. If f of x is 2x plus 1 and g of x is the square root of x, then the composition would be f of g of x, where we take the f function, which is 2x plus 1, and we substitute the g function in its place, which is the square root of x. So we took out this x and substituted in the function g of x in its place. This is known as a composition function. The operations on functions, we can add, subtract, multiply, and divide functions by adding the function to another function, by subtracting g of x from f of x, by multiplying f of x times g of x, that's multiply, not compose, and by dividing f of x and g of x, as long as g of x is not 0. It's important to note that the domains of the sum, difference, product, and quotient consist of the x values that are in the domains of both f and g. Also, the domain of the quotient function doesn't contain any x value that leads to the denominator being 0. So let's give that a try by looking at adding and subtracting functions first. Here we want to add f of x and g of x together. So f of x plus g of x is going to look like 2x squared plus 8 plus x minus 3. And because it's addition, we really don't need the grouping symbols, but you can write them if you would like to begin. So combining like terms, we only have one x squared term, one x term, and then we have 8 minus 3, so 8 minus 3 is 5. Now let's go back and talk about the domain of the sum. Since both f of x and g of x are a linear function and a quadratic function, the domain is all reals on both of those. So we are going to have the domain on the composition also be all real numbers. When we look at part B, f minus g of x, you got to be careful with the subtraction. So 2x squared plus 8 is our f function, and we're going to subtract the entire g function. So here you've got to distribute the subtraction through the g function, which is going to give us minus x and plus 3. So combining like terms, 2x squared minus 8x, and now we're adding 8 and 3 for 11. But again, the domain is going to contain all real numbers since this is a parabola, and parabolas are continuous everywhere. In example 2, we have f of x as a parabola and g of x is a linear function, and we want to multiply f times g. So again, f of x is continuous everywhere, the domain is all reals. G of x is continuous everywhere, the domain is all reals. We're going to multiply the two together, and we'll end up with a cubic function, so that domain should be all reals as well. Multiplying 3x squared times this polynomial, we have 9x cubed plus 3x squared. Multiplying negative 11x times this binomial, we have negative 33x and negative 11x. Multiplying negative 4 by our binomial gives us negative 12x and negative 4. Combining like terms, we'll find 9x cubed, and then, let's see, I got a 3x squared. I should have another, this is 30x squared. Missed the square right there. So 3x squared minus 33x squared is minus 30x squared. 11x minus 12x is negative 23x minus 4. So our product of f times g is a cubic polynomial, and the domain is going to be all real numbers for our product. And then in example B, we're looking at dividing g into f. So the f of x is 3x squared minus 11x minus 4, and g of x is 3x plus 1. So this is f divided by g. If we factor the numerator, we'll have 3x plus 1 times x minus 4, and we're dividing by 3x plus 1. So we know that the denominator can't be 0, but the denominator cancels, and we end up with only a line. Now the line is continuous everywhere, but we have this restriction from the very beginning that we can't have negative 1/3 in our domain for g. That makes the restriction for our quotient go from negative infinity to negative 1/3. There's going to be a hole there. This creates a hole. When we cancel, that creates a hole in the graph. And then from negative 1/3 on to infinity. So our domain has one issue at negative 1/3. In this image, we're looking at the behavior for the output of the first function becomes the input of the second function. And you can see at the final result, we're composing g of f of x. So written out the g of f of x, the g of f of x. We want to put the input, or our x value for the f function, becomes the y value for f. And that y value for f, once you know that, you substitute that into the g function. That now becomes the input of the g of x. And then when you evaluate it, we get the value for the composition of the g of f of x. Let's be sure we understand using the notation. Here you can see the g of f of x can be combined to look simpler in that format. Same thing with the f of g of x. We can rewrite that as f of g of x. So this little open circle symbol is not multiplication. Don't confuse it with that. It's really substitution. And when you see either this symbol or this notation, you want to read that as f of g of x. That's the proper way to read that. Let's get an example here. Let's say we have f of x is x squared minus 3, and g of x is x minus 1. In either case, so you can see that I'm talking about substitution. If I want to know what the f of 2 is, then I would simply substitute 2 in place of my x in the function x squared minus 3. And then do the order of operations. We have 4 minus 3, and that would be 1. So the f of 2 is 1. This way I can use that output for the f of x and substitute that back into the g of x. And by doing that, we're going to find out that the g of f of 2 is the g of 1, and the g of 1 is x minus 1. So 1 minus 1. The g of f of 2 is going to give us the 0. Likewise, we can also do the f of g of x. Let's give that a try. So the f of x is my outside function. That's this one with the star. My outside function is x squared minus 3. So where my variable is, I just left a spot there for my substitute. And then we're going to substitute in to the f function. We're going to substitute the g of x, and the g of x is x minus 1. That takes the place of this x in our function f. Now if I want to expand that, the f of g of x is going to be x squared minus 2x plus 1, so I've distributed this binomial, and minus 3, and combining that together we have x squared minus 2x minus 2 for the f of g of x. So whichever way you compose it, you can simplify and combine terms using that composition rule. So let's give it a try here in example 3. First, in both cases, we're going to find the f of g of negative 3. The first method we want to use is that we are going to find the g of negative 3. We're going to do that first. So the g of negative 3 is going to be negative 3 minus 4, which is negative 7. And since the g of negative 3 is negative 7, the f of g of negative 3 is equivalent to the f of the y value, that output, negative 7. That becomes, negative 7 becomes the input into the f function. So we want to find the f of negative 7 by substituting negative 7 for our variable and adding 2, which is 49 plus 2, so we get 51. The f of negative 7 is 51, or the f of g of negative 3 became the f of negative 7, which worked out to be 51. Now, if this method holds true, we should get the same answer for part B. So in part B, first we're going to do the actual composition, and we'll find the function f of g of x. We'll do that first. So using our notation correctly, the f of g of x tells us to write down the f function, which is x squared plus 2, and in place of the x, we're going to substitute the g function, which is x minus 4. Expanding that binomial is x squared minus 8x plus 16 plus 2 more. But you see how this is more complicated. So I'm happy to stop at the previous step. That just turns it into a simpler problem for substitution. And then from this answer, we'll substitute what we're looking for. And that's our x value here. So we want to substitute negative 3 for our variable. So the f of g of negative 3 is negative 3 minus 4 quantity squared plus 2, which is negative 7 squared plus 2, which again turns out to be 51. Either method works. It just depends on which you find the most friendly. In example 4, we're looking at a practical application. If a store is offering a 15% discount on all items and employees get a 20% employee discount, we want to write composition functions for the following. We're going to call C of X the 15% discount. So C of X is whatever the price of an item is, and we're going to take off 15% of the price of that item. So I'm letting X represent the price of some purchased item. So we have 1 minus 15, that's going to be 0.85 of the price of the item. And the 20% discount for employees, we're going to call that E of X. That would be the price of the item minus 20% if you're the employee. So you're going to pay 0.80 of the price of the item. Now for part A, to model taking the 15% discount and then taking the 20% discount. Well, we know the employee discount is 0.80, so we want to take the employee, so the cost of the item is 0.80, and we're substituting the 0.85 next. So you can say we took the 20% discount after we took the 15% discount. We did this first and then the 20% second. So the employee is going to get 0.68 of the price of the item. In part B, we want to model taking the 20% discount first and then the 15% discount. So to model taking the 20% discount and then the 15% discount, we would have the C of E of X, and that would be 0.85 times 0.80. So the customer price is 0.85. That would be the outside, and we want to do the 20% first. That would be the inside. So the C of E of X, do you see what's happening? It's 0.68x. If we compare the two, if you were an employee, which discount would you take first and why? And if you think about it, there's really no benefit because multiplication is commutative and associative. The discounts are the same, so you can write some sentence that makes sense to you. I'm going to say there is no benefit. Mathematically, we know because multiplication is commutative and associative, so it doesn't matter which one comes first. It's going to give you the same discount. Okay. So moving on to our last problem. If your teacher offers a whole class bonus if everyone passes the next math test, the teacher says she will give everyone a 10-point bonus and increase everyone's grade by 9% of their score. So here in example A, you earned a 75 on the test. Would you rather have the 10-point bonus first and then the 9% increase, or the 9% increase first and then the 10-point bonus? So let's figure that out mathematically. I'm going to use B of X to represent the bonus. So the bonus equation we're going to say is B of X. So the teacher said whatever our score is, she would give us 10 points. And then the other approach would be the scoring method. So the scoring method, we're going to call that S of X. That would be whatever your score is and 9% added. So that would be 1.09 of X. So when we compose, if we do the S of B of X or the B of S of X, which one turns out to be the best? So let's say we get the bonus first, so that would be 1.09 of the bonus, so x plus 10, which would be 1.09x, so 1.09x plus 10.9. So this is the bonus first, and then the 9%. And then the other one, method 2, would be the 9% first, and then the bonus. So the 9% first would be 1.09 in place of the x plus 10 points. So between the two, this one or this one, which would be the best way? And I believe it's going to be this is the best one. We want this way, since it's 9/10 of a point more than the alternate method here. So we want to use the bonus first and then the score. And then to explain that, I would say, yes, this is the best way. The 10-point bonus, I want to say yes, the 10-point bonus first gives every student 9/10 of a point more than the other method. Gives every student 0.9 of a point more than the other option. And that's the end of lesson 6. See you next time.